Introduction to Recursion, Methods that Call Themselves. Welcome everybody to Introduction to Recursion lecture. Let's first go over what recursion is, the definition. So just recursion in general, the definition is the process of repeating in a self-similar fashion. Or you can also say object that contains self-similar smaller copies of themselves are recursive. So we can see this is one of the meme picture that is famous that describes what recursion is, where we can see recursion a lot among nature, math, language, art, music, and programming. Can you think of any examples of recursion? For those of you watching this recording, please pause and think about a couple of examples. Recursion in nature. You can see the recursion example a lot in nature. I have a couple examples. Snowflakes definitely shows a pattern that is replicated in smaller details on the same arm. So you can see that we have this snowflake big pattern, and then there's this replicated pattern in a smaller detail. Another would be the coastline. So it's similar to snowflake, there's this pattern of coastline that is replicated in smaller detail. You will see that patterns will just repeat at different scales. And we have some vegetables that has this repeating patterns and so on. Recursion in art. I'm not well versed in art, but when you look up recursion in art, there you can find like multiple different pieces that uses recursion. You can see this is like a repeating chair. So we've just looked at recursion in general, but what is recursion in programming? So recursion in the context of programming is the process of defining a problem in terms of itself. And when we talk about recursive programming, we are writing methods that call themselves to solve problems recursively. And recursion in programming is an equally powerful substitute for iteration, which is often called as loops. So why are we learning recursion? Why is recursion important? There are numerous reasons, but one of the reasons is the recursion problems are asked in coding interviews a lot. And why are they asking that recursion problems a lot? It's because recursion problems are often used in many classic algorithms, particularly in divide and conquer, dynamic programming, and backtracking strategies. These you may or may not be familiar with, which will be covered in subsequent lectures. And recursive solutions can be more elegant and simpler than their iterative counterparts. especially for problems related to tree structures. Yeah, whenever you're dealing with tree structures, it's just inevitable you would need to use recursive solutions. And one of the algorithms you can use is step first search. If you use recursion, it's definitely simpler. And there are just problems that have a naturally recursive pattern. And additionally, some problems are just inherently recursive. Uh, the two examples would be traversing a tree data structure and exploring graphs. So let's go over the structure of recursive problems. So recursive problems in general have two portions. First is a base case, and second is recursive case. So what is base case? Base case is a case within a recursive solution that is so simple it can be solved directly without a recursive call. And then what is recursive case? It's a case within a recursive solution that involves reducing the overall problem to a slightly simpler problem of the same kind, one that can be solved by a recursive call. So this may not make sense at the moment. So let's use an example of Russian nesting doll. So let's imagine a large Russian nesting doll uh, as shown in this picture. We can see that inside this large Russian nesting doll, there is a smaller doll of the same type. And inside that one, there is even smaller doll and so on. So you can think of the process of opening each doll and finding a smaller one inside is similar to a recursive function calling itself with a smaller problems. So this would be similar to a recursive case. As you can see, uh, a case within a recursive solution that involves reducing the overall problem to a slightly simpler problem. So overall problem could be thought of as the largest Russian nesting doll, and slightly simpler problem would be the Russian nesting doll that is smaller inside, and then eventually you will reach to the smallest doll, and this smallest doll cannot be opened. This represents the base case in recursion, where the recursive process stops. So this is base case. A case within a recursive solution that is so simple, it can be solved directly without a recursive call. So using this Russian nesting doll, let me go over recursion steps. So we can do recursion problems in 4 steps. First is problem division, second is simpler problem, third is base case, fourth is solution assembly. So first, you open the first stall, which is same as calling a recursive function with the initial problem. And then you are now faced with a smaller doll, You can think of this as simpler problem, and you open it, and you open it again until you reach base case, which is the smallest doll, can't be opened. So in recursion, this is base case. So no further recursive calls are made. And lastly, solution assembly. When you reach to the base case, when you get to the smallest doll, you would want to assemble the dolls back together. Recursive function would need to have solution assembly step to assemble the solution from the base case to upwards. So here is a sample problem, which is printing 5 stars iteratively. We are doing this iteratively. We're not doing this recursively. You may already be familiar with printing 5 stars iteratively. When we print 5 stars, I mean by you need to print 1 star at a time. So to do that, you will need to use a for loop and then print 1 star 5 times. This is a simple problem that can be solved easily with loop. What about solving this recursively? This would be a good way to understand. So let's look at this and let's kind of follow the step that we talked about. You can define the desired function, which is print stars, and then this input n represents the number of stars. Then we would be in a problem division step. So we would, in our main function, we would call print stars with n being 5. And then when we call print stars with our initial value of n, this will call print stars, and in print stars, we would be skipping this if condition because n is not 0. So we would print star, and then we would call print stars again with n minus 1. N in this context is 5, so the print stars that we're calling next would be print stars 4. You would continue this print stars 4, print stars 3, print stars 2, print stars 1 until you reach n equals 0. When n equals 0, there will be no further recursive call made, and we're printing nothing. This one, because problem is so simple and we're printing the star right to our terminal using system out print, no solution assembly step is necessary because we don't need to assemble the solution from the base case upward. Instead of printing stars, if we were to return stars in string, then there will be a solution assembly step, but for this one, no. Stack memory stores function data for pending functions. So you might be wondering what actually happens when we call the same function over and over again with differing input. So let's look at this call hierarchy. We start with main, and function 1 gets called, function 2 gets called, function 2 calls function 3, function 3 calls function 4. You can think of this as, for this previous example, main would call print stars 5, print stars 5 will call print stars 4, and so on. Then each function will create will have its own stack, and each stack frame, what happens is it stores any local data, parameters, and return address in calling function. So print stars 5 will store n as 5, print stars 4 will store n as 4, and it's not visible to us, but you will be able to see that return address to previous function that is calling this new function. And then in your computer, there is this thing called stack in your memory, and functions are pushed onto the stack when a function call is made, and they get popped off when the function is completed. Tracing recursion. So we looked at print stars. Now let's look at this following recursive method. We have this function called method called mystery, and can you kind of in your mind calculate what will be the result of the following call with n being 640A? For those of you watching this video, please pause and try to get the result of the following call. Here is the result. At first, we are calling mystery with n value being 648, and our a will be n divided by 10, so we will have 64. You may be wondering why is it not 64.8? It's because we are our value a has type integer, so we're doing integer division, so the decimal value gets dropped. And then b does 648 modulo 10, so the remainder value is 8. If we return mystery with 8 plus b, that means it's 64 plus 8. So we're calling mystery 72, and we'll just repeat this step. A comes out to be 7, B comes out to be 2, and then we're calling mystery with 7 plus 2. 7 plus 2 is 9. And when we call mystery with 9, we are returning 9 immediately. It's because 9 is less than 10, so we're just returning n as it is. Common uses for recursion. So solving certain kinds of problems that lend themselves well to this approach would be Towers of Hanoi, folder crawlers, or traveling problems, 8 queens. For those of you interested in these problems, please look up online. There are really interesting problems that a lot of folks kind of looked into it. So you'll be able to find a lot of examples. And if you're working with tree data structures, you will get to use recursion a lot. And if you're working with fractals, then you will need to use recursion because most fractals have recursion at their core. Here is a sample problem finding factorial. So just to give a recap on what factorial is, the factorial of a number n is the product of all positive integers less than or equal to n, which means if you have 1 factorial, that's 1, 2 factorial is 2 times 1, 2, and 3 factorial is 3 times 2 times 1, 4 factorial is 4 times 3 times 2 times 1, and so on. So this is one of the problems that can be solved nicely with recursion. So we can define the desired function. This one, I'll give you this first one. Let's name the desired function to be a factorial that receives integer n value and returns integer. Then we looked at problem division, simpler problem, base case, solution assembly steps. Let's try this. So for those of you watching this recording, please pause and work on this factorial problem. Here is a sample solution to this factorial problem. So we have main and also factorial method. So our main will define what the initial value n should be, and I just set n to be 5, and then factorial, we're calling factorial with n value, and this factorial will have base case and recursive case. So base case would be the n value that is so simple, you don't have to do the recursive step, which would be n being 0. When you have 0 factorial, the value is 1. Otherwise, if n is greater than 0, you can call n times factorial and then pass n minus 1 as an input parameter value. Here is another problem, Fibonacci sequence. Say Fibonacci sequence is a series of numbers where each number is the sum of the 2 preceding ones, usually starting with 0 and 1. And the sequence goes 0, 1, 1, 2, 3, 5, 8, 13, 21. You can see that we're adding 0 and 1 to get 1. We're adding 1 and 1 to get 2. We're adding 1 and 2 to get 3. We're adding 2 and 3 to get 5. So let's try solving this. For those of you watching this recording, please pause and work on this. Here is a sample solution. We have a main, and we're for this example, we're setting n to be 9, and we're calling Fibonacci method with n being 9 as our initial value. And then if we look at this method, we can see that base case is, there are two base cases, n being 0 and n being 1. So if n is 1, you would return 1. If n is 0, you return 0. And the recursive case would be, unlike what we've seen previously, this one will call functions twice. So if we have Fibonacci n, we will call Fibonacci n minus 1 and Fibonacci n minus 2. Now let's talk about different types of recursion. There are three types of recursion: direct recursion, indirect recursion, tail recursion. So direct recursion is what we saw in previous slides, which is a method that is calling itself directly. Indirect recursion is method that calls another method that in turn calls the original method. We will show you an example of this in subsequent slides. And tail recursion is if the recursive call is the last operation in the method. This is often used for efficiency reason. So direct recursion, as we said, please refer back to factorial example. A method factorial directly calls factorial n minus 1. Indirect recursion, this occurs if a method calls another method and another method calls the first method. And by doing that, it will be we'll be creating this recursive cycle through several function calls. And one of the simple example is shown here, is odd and even. So we have this main, and main is calling is odd method, and is odd method is calling is even, and is even is calling is odd, so on until n reaches 0. So this is an example of indirect recursion because recursive cycle occurs through several function calls of is odd and is even. Tail recursion, this occurs when the recursive call is the last operation in the function. Unfortunately, in Java programming language, tail recursion doesn't work, so we will not cover this in this lecture. Then what are downsides, pitfalls of recursion? Two things, stack overflow and performance issue. So if the recursion, if there are just too many recursive steps, then it can cause a stack overflow due to too many frames being added to the call stack. We saw the example of how whenever you call function, it just stacks up into your memory. So if too many of them are there, it's just going to cause this stack overflow error. And you can definitely recreate this issue by calling Fibonacci with n being sufficiently large. And another issue is that recursive solutions can be less efficient and more memory intensive than iterative solution because you just need to create a new call stack for every function call you make. So here is a duplicate calculation in recursion. So let me show you a Fibonacci example. Please feel free to draw, but you can see that when we are trying to get Fibonacci value with input n as 4, this can be represented as Fibonacci 3 plus Fibonacci 2, and Fibonacci 3 can be represented as Fibonacci 2 plus Fibonacci 1 plus Fibonacci 2. So we can see that we are calling Fibonacci value 2 twice in Fibonacci 4. If you try breaking Fibonacci value, you will see that for higher Fibonacci n value, there will be more duplicate calculation that will be done. And how can we eliminate the duplicate calculation? This technique is called memoization. What you're basically doing is, instead of recalculating, you are storing the intermediate results in the cache so that you can reuse them later without calculating over again. And here's an example of Fibonacci with memoization. So the only change that's done is we are importing HashMap library, and then we are using creating HashMap to store key and value that are integer value. And whenever we are calling Fibonacci n, we will check whether we already calculated that value. If so, then we will just return that value from cache instead of going through the recursive step. And whenever you calculate results, you will keep the result in cache so that next time, if you happen to call Fibonacci with the n value that you already calculated, it can just return from cache right away. That's everything I have for introduction to recursion. Thank you, everyone.